Overview Part 1, Datapaths Part 2, A Simple Computer. Introduction. Datapath Example. Arithmetic Logic Unit, ALU. Shifter. Datapath Representation and Control Word. Part 2, A Simple Computer. Part 3, Multiple Cycle Hardwired Control. Introduction. Computer Specification. Instruction Set Architecture, ISA, the specification of a computer's appearance to a programmer at its lowest level. Computer Architecture, a high-level description of the hardware implementing the computer derived from the ISA. The architecture usually includes additional specifications such as speed, cost, and reliability. Introduction, continued. Simple computer architecture decomposed into Datapath for performing operations, Control Unit for controlling datapath operations. A datapath is specified by a set of registers, the microoperations performed on the data stored in the registers, a control interface. Datapaths guiding principles for basic datapaths, the set of registers. Collection of individual registers. A set of registers with common access resources called a register file. A combination of the above. Microoperation implementation. One or more shared resources for implementing microoperations. Buses, shared transfer paths. Arithmetic Logic Unit, ALU, shared resource for implementing arithmetic and logic microoperations. Shifter, shared resource for implementing shift microoperations. Datapath Example 4 Parallel Load Registers. 2 mux-based register selectors. Register Destination Decoder. Mux-B for external constant input. Buses A and B with external address and data outputs. ALU and shifter with mux-F for output select. mux-D for external data input. Logic for generating status bits V, C, N, Z. Datapath Example, performing a microoperation. Microoperation, R0 R1 plus R2. Apply 1 to load enable to force the load input to R0 to 1 so that R0 is loaded on the clock pulse, not shown. The overall microoperation requires 1 clock cycle. Apply 0 to MF select and 0 to MD select to place the value of G onto bus D. Apply O1 to A select to place contents of R1 onto bus A. Apply OO to destination select to enable the load input to R0. Apply 10 to B select to place contents of R2 onto B date 2 and apply 0 to MB select to place B date 2 on bus B. Apply O10 to G select to perform addition G equals bus A plus bus B. Datapath Example, Key Control Actions for Microoperation Alternatives. Perform a shift microoperation. Apply 1 to MF select. Use a constant in a microoperation using bus B. Apply 1 to MB select. Provide an address and data for a memory or output write microoperation. Apply 0 to load enable to prevent register loading. Provide an address and obtain data for a memory or output read microoperation. Apply 1 to MD select. For some of the above, other control signals become don't cares. Arithmetic Logic Unit, ALU. In this and the next section, we deal with detailed design of typical ALUs and shifters. Decompose the ALU into an arithmetic circuit, a logic circuit, a selector to pick between the two circuits. Arithmetic circuit design. Decompose the arithmetic circuit into an n-bit parallel adder, a block of logic that selects 4 choices for the B input to the adder. See next slide for diagram. Arithmetic circuit design, continued. There are only 4 functions of b to select as y in G equals a plus y. b. 1. What functions are implemented with carry into the adder equals 0? Equals 1. Sin equals 0. Sin equals 1. G equals a. G equals a plus 1. G equals a plus b. G equals a plus b plus 1. G equals a plus b. G equals a plus b plus 1. G equals a 1. G equals a. Arithmetic circuit design, continued. Adding selection codes to the functions of b. The useful arithmetic functions are labeled in the table. Note that all 4 functions of b produce at least one useful function. Plus, 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 plus. Logic circuit and or not 000111101. The text gives a circuit implemented using a multiplexer plus gates implementing AND, OR, XOR and NOT. Here we custom design a circuit for bit Gi by beginning with a truth table organized as a K-map and assigning S1, S0, codes to AND, OR, etc. Gi equals S0 by plus S1 by plus S0 by plus S1 S0 Gate input count for mux solution greater than 29. Gate input count for above circuit less than 20. Custom design better. S1 S0. AND. OR. XOR. NOT. I by. 0 0. 0 1. 1 1. 1 0. 1. Arithmetic Logic Unit, ALU. The custom circuit has interchanged their S1, S0, codes for XOR and NOT compared to the MUX circuit. To preserve compatibility with the text, we use the MUX solution. Next, use the arithmetic circuit, the logic circuit, and a two-way multiplexer to form the ALU. See the next slide for the bit slice diagram. The input connections to the arithmetic circuit and logic circuit have been assigned to prepare for seamless addition of the shifter, keeping the selection codes for the combined ALU and the shifter at 4 bits. Carry in C and carry out C plus 1 go between bits I and by are connected to both units. A new signal S2 performs the arithmetic/logic selection. The select signal entering the LSB of the arithmetic circuit, SIN, is connected to the least significant selection input for the logic circuit, S0, Arithmetic Logic Unit, ALU, continued. The next most significant select signals, S0 for the arithmetic circuit and S1 for the logic circuit, are wired together, completing the 2 select signals for the logic circuit. The remaining S1 completes the 3 select signals for the arithmetic circuit. Combinational shifter parameters. Direction, left, right. Number of positions with examples. Single bit. 1 position. 0 and 1 positions. Multiple bit. 1 to n, 1 positions. 0 to n, 1 positions. Filling of vacant positions. Many options depending on instruction set. Here, we'll provide input lines or 0 fill. 4-bit basic left/right shifter. 3. I. R. L. S. Serial. Output L. Output R. 2. 1. H. M. U. X. Serial inputs. IR for right shift. EL for left shift. Serial outputs. R for right shift, same as MSB input. L for left shift, same as LSB input. Shift functions, S1, S0, equals 00 pass B unchanged, 01 right shift 10 left shift 11 unused. Barrel shifter. D. 3. S. 1. M. U. X. 2. Y. A rotate is a shift in which the bits shifted out are inserted into the positions vacated. The circuit rotates its contents left from 0 to 3 positions depending on S. S equals 00 position unchanged, S equals 10 rotate left by 2 positions, S equals 01 rotate left by 1 positions, S equals 11 rotate left by 3 positions. See table 10 to 3 in text for details. Barrel shifter, continued. Large barrel shifters can be constructed by using layers of multiplexers. Example 64-bit. Layer 1 shifts by 0, 16, 32, 48. Layer 2 shifts by 0, 4, 8, 12. Layer 3 shifts by 0, 1, 2, 3. See example in section 12-2 of the text. 2-dimensional array circuits designed at the electronic level. Datapath representation. Have looked at detailed design of a Lewin shifter in the datapath in slide 8. Here we move up one level in the hierarchy from that datapath. The registers, and the multiplexer, decoder, and enable hardware for accessing them become a register file. The ALU, shifter, MUXF and status hardware become a function unit. The remaining muxes and buses which handle data transfers are at the new level of the hierarchy. Address out, data out, constant in, MB select, bus A, bus B, Fs, V, C, N, Z, MD select, N, D data, write. D address, O address, B address, A data, B data, 2, M, X, register file, A, B, function, unit, F, 4, mux B, 1, mux D, day 2 in. Datapath representation, continued. In the register file, multiplexer select inputs become A address and B address. Decoder input becomes D address. Multiplexer outputs become A data and B data. Input data to the registers becomes D data. Load enable becomes write. The register file now appears like a memory based on clocked flip-flops. The clock is not shown. The function unit labeling is quite straightforward except for Fs. Address out, data out, constant in, MB select, bus A, bus B, Fs, V, C, N, Z. MD select, N, D data, write, D address, O address, B address, A data, B data, 2, M, X, register file, A, B, function, unit, F, 4, mux B, 1, mux D, day 2 in. Definition of function unit select, Fs, codes, G, select, H, select, and, MF, in T, of, Fs, codes, Fs 3:0, MF, select, G, Select 3:0. H. Mica. O operation. O 20. 0001. 0010. 0011. 0100. 0101. 0110. 0111. 1000. 1. X. 00. 1001. 01. 1010. 10. 1011. 11. 1100. 4x. 1101. 1110. FA. Negation. FA. Plus. B. Dash. F. A. AB. U grave. U acute. Senior. SL. A-ring. Boolean. Equations. MFS equals F3 F2. Xi equals phi. Xi equals phi. The control word. The data path has many control inputs. The signals driving these inputs can be defined and organized into a control word. To execute a micro instruction, we apply control word values for a clock cycle. For most microoperations, the positive edge of the clock cycle is needed to perform the register load. The datapath control word format and the field definitions are shown on the next slide. The control word fields: DA-D address, AA-address, BA-B address, MB, MUX B, Fs, function select, MD, MUX D, RW, register write. The connections to datapath are shown in the next slide. Control word: D, A, AA, BA, M, B, Fs, R, W, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Control word block diagram. 10, 8, 14, 13, 11. Bus D. Constant in. N. Mux B. 1. D data. Write. D address. O address. B address. A data. B data. X. Register file. A. B. Function. Unit. Mux D. Data in. Bus A. Bus B. R. W. 12. AA. 15. D. BA. 9. Address out. Data out. V. C. N. Z. 7. MD. MB. 6. 4. Fs. 5. 3. 2. Control word encoding. Encoding of control WROOO register F negation OOO. AA. B. A. MB. Fs. MD. R. W. Function. Code. Function. Code. Function. Code. Function. Code. Function. Code. R. O register F negation A O function no right R 1 1 constant 1 FA negation plus 1 1 data in 1 right 1 R 2 10 FA negation plus B 10 R 3 011 FA negation plus B plus 1 0011 R 4 100 FA negation plus B 0100 R 5 101 FA negation plus B plus 1 0101 R 6 110 FA negation dash 1 0110 R 7 111 FA negation 0111 FA negation U grave B 1000 FA negation U acute B 1001 FA negation A ring B 1010 F negation 1011 A FB negation 1100 F negation senior B 1101 F negation SL B 1110 Microoperations for the Datapath Symbolic Representation W R 1 negation R 2 dash R 3 R 1 R 2 R 3 R E G ISTA FA equals plus plus B 1 F unction right R 4 negation S LR6 R 4 R 6 R E G ISTA F equals SL B F unction right R 7 negation R 7 1 plus R 7 R 7 register FA equals plus 1 function right R 1 negation R 02 plus R 1 R con S tant FA equals plus B func DO N. Right. Data out. Negation. R. 3. Dash. R. 3. R. E.g. I. S. T. E. R. N. O. W. R. It. E. R. 4. Negation. D. Atta in. R. 4. Dash. Data in. Right. R. 50. Negation. R. 5. R. 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 E. G. Ista. FA. Equals. A-ring. B. F. Unction. Right. Microoperations for the datapath, binary representation. Microoperations from T. A. Binary C. O. O. Results of simulation of the above on the next slide. Mica. O. O. P. Ratio. N. D. A. B. M. F. S. R. W. 1. 011. 010. 10. 20. X. 110. 111. 11. 30. 000. 00. 001. 11. 101. 2. 3. Dash. Negation. 4. S. LR6. 7. 71. Plus. 02. Data out. Atta in. 50. Datapath Simulation.